Engineering at Northwestern University with a courtesy appointment in mechanical engineering. She is Associate Director of the Northwestern Argonne Institute of Science and Engineering, also the Associate Director of Northwestern Center for Engineering, Sustainability, and Resilience. Her research is about emerging technologies, their energy and environmental impacts, and their potential for influence greenhouse gas emissions, water consumption, and energy consumption at the economy-wide level. And so she does a lot of work with techno-economic analysis and life cycle analysis, and we went into details about that this morning during the experiential seminar. She has a PhD in chemical engineering from the University of Michigan and a bachelor's also in chemical engineering from Purdue University. She had a very, very interesting career spanning not just academia, but also national labs and consulting. Currently, again, we talked about it this morning, but today she's focused on her one of her projects. So thank you very much.
Well, it's really a pleasure to be here this afternoon. So this is the first trip I've taken in quite some time. And it's just been really a pleasure to meet so many great people and share meals and just reconnect with the whole academic community. So thanks for having me very much. So my talk this afternoon is going to review 3 different case studies from our recent work within my group, in which the objective of these case studies is to illustrate different ways that we use analysis to set guardrails and guideposts that can help guide us along the energy and material transitions that we're going through. And this is the first time I ever used this slide again, so I'm going to test it. But we did test it, and I'm going to give up. Maybe it's like not.
Touch the screen.
Try again. Let me try this one. Okay, I'll just use the laser pointer. Okay. So before I get into these case studies, I just wanted to provide a little bit of an overview of my research group at Northwestern. So we work generally in these 5 areas. And I'll talk about most of these today with the exception of the water area. So in this area, we're doing work around evaluating desalination technologies and also nutrient recovery technologies for wastewater treatments. But otherwise, our work tends to focus on bioeconomy, also plastics, sustainable fuels, and circular economy. I'd like to just acknowledge the members of my research group who, of course, do all the work that we present in these seminars. And so I'm very fortunate to work with these people. So I have 6 postdocs in group, 3 PhD students, and one master's student. So we're all working on these different projects together. Before I get into the case studies, I just wanted to set the stage a little bit for these material energy transitions. Even though I know that, I'm in this department, right? I'm in an energy and water seminar, so many of you are familiar with these transitions, but I think it's still helpful to provide a little background. So one of the transitions that's, of course, most sort of in the forefront, especially recently, is our transition to electric vehicles from combustion engine vehicles that rely on gasoline. This is primarily happening in the light duty space. And there have been many analyses done to try and project how will EVs take over or increase in usage. And so, of course, depending on who you ask and what their particular assumptions are, you will get different numbers. So I just use this figure as an example of how different entities are projecting the particular year-on-year oil demand growth for petroleum. And in this particular slide, we have examples from OPEC and from the International Energy Agency. These are the blue dashed lines leading to the left-hand axis. And you can see that both of these groups, they project an eventual decline in the demand for oil, or the demand in oil growth. But they both kind of come to the conclusion that things will level off later this decade. Meanwhile, we have two different energy forecasting groups and then two oil companies projecting how the oil consumption will be displaced by the use of electric vehicles in million barrels per day, right to the right-hand axis. And these all increase, again, depending on who you ask. The oil companies have the lowest projections for this change, but some of the energy analyst firms have much higher projections. But you could take this to mean that roughly towards the end of the decade, we're saying, is this peak oil demand? Who knows? Probably not. But nonetheless, this is a transition that we're undergoing. And the question is this really enough? Is decarbonization of the light-duty fleet through electrification enough? And if not, what else can we bring to bear as we go through this transition to improve our progress towards decarbonization? In terms of material transitions, there's also a lot of calls for rethinking how we do plastics. And this does tie back to our sector, of course, but there's a lot of demand for achieving a 100% circular economy, which is probably impossible because there will always be leakage, but advancing towards a circular economy for plastics. So this is a recent binding agreement proposed in Science this year. But as we think about how will we make a plastics system that is circular, this could likely involve new chemistries, new feedstocks. It could involve different processing methods and then different recycling methods. These will all have an influence on the overall sustainability of the circular economy. And it's not a given that something that's circular will be sustainable. So there's a role for analysis here in determining what are the implications of some of these choices that we make as we advance towards circularity. And so to me, these are sort of two examples of role or places where analysts have a role to play in helping guide technology development and also helping guide policy development, in part to help spur policy development, but also to help spur the societal changes we need to achieve decarbonization and other sustainability goals that we have. So in our group, we set out to try and serve that role as analysts, and we use a number of different tools to do that. And we apply those tools to the 5 different areas I mentioned earlier. And in so doing, what we really hope to provide is both guardrails and guideposts to technology developers and to policymakers. Guardrails in the sense of we want to know how far, so one way a guardrail can be used is how far can we push things before we're going to fall off a cliff. And the other way a guardrail can be used is what's the maximal benefit that we expect we can achieve? Can we even get close to where we want to be with the maximal benefit that we can derive from a particular technology? And if you have those two boundaries established, then you need markers along the way to help you understand for any given technology, what are the advances that we need to make them cost effective, to make them energy efficient, kind of break down these technologies into their component parts, their component unit operations, and provide guidance to technology developers, for example, to increase energy efficiency within a reaction or to improve water recycling within a certain technology. So these are the types of guidance that we strive to give. And the first example that I will give is really more of a guardrail example. And it ties back to that first transition that I mentioned, which is electrification of the light-duty fleet. So even if we are able to electrify the light-duty fleet entirely, there are transportation sectors that are much harder to decarbonize. These include aviation and the marine sector and heavy-duty trucking. We just need, the energy density of liquid fuels are very well utilized in these spaces. They're hard to electrify. So the question is, how can biomass and waste resources contribute to the decarbonization of these sectors? So this is something we set out again to be more of a guardrail analysis, like how far can we get with our application of biomass? So I've spent at least a decade looking at biofuels, primarily doing life cycle assessments. And I've kind of over the course of that decade come to the sort of general conclusion that biofuels are low carbon fuels. In general, they offer greenhouse gas benefit compared to fossil fuels, largely because of the biogenic carbon that these fuels contain. It's not true for every case, but in most cases, biofuels are either lower carbon or could be engineered to be such. So we have, the nice thing about biofuels is that there are many different fuels that we can make by many different pathways and using different feedstocks. So when we think about pushing towards decarbonization of these harder to decarbonize sectors, we have a number of fuel choices at our disposal, a number of different reaction pathways, but we also have a number of different technology readiness levels. Some technologies are pretty much ready in the near term, but some are going to need to wait for to bring into the markets and start contributing to the fuels that we have available to us. And what we set out to do is to evaluate these different options for using these different fuels, using what could be the biomass resource that we have in the United States. So the US, we have a lot of land in this country. And in 2016, the Department of Energy set out to understand what would need to be achieved to get us to 1 billion tons of biomass. It's an aspirational number pretty much, but looking at where can we produce this biomass, how can we produce it sustainably, and what would we have on hand if we were able to produce 1 billion tons of biomass. And they consider different scenarios in this report. One of them is a business as usual scenario, where we're kind of just chugging along as we are now. But then if biomass were to become more valued, and they set 2 different price points in this study, $40 per dry ton and $60 per dry ton, we could expect to see a response from the markets and a lot more biomass provided. So if you look at the difference between the business as usual and the 1 billion ton scenarios, we have more agriculture feedstocks and more forestry and wood feedstocks, but clearly where the bump comes in is in the energy crop area. And at the energy crops that we're talking about here are energy grasses like miscanthus and switchgrass. These are very high yielding grasses, and they tend to enable the sequestration of soil carbon. So they kind of pump carbon into soils. And so there's an opportunity to build up our soil carbon base for using these energy crops. Additional energy crops are short rotation woody crops, and these are poplar and willow, for example. So these are examples of different types of crops that might come more online if we really wanted to go in this direction. So the question is, well, let's say we have this biomass, how should we use it? So in our work, we developed 3 different scenarios, again, to kind of try and put some boundaries on what we might expect the benefits to be from this deployment. And these 3 scenarios start off with what I call the no favorite scenario. So for the marine sector, aviation sector, and the heavy duty sector, kind of spread the biomass evenly across them. And so every year, the blend level of biofuel in those sectors is roughly the same, and it increases similarly over time. In the second scenario, we call this the low-hanging fruit scenario because we prioritize aviation for biomass. The aviation industry, they only have so many options for decarbonization, and low carbon fuels is one of them. They've been an early adopter of biofuels. I'm sure you've all seen press releases. United flew with biofuel, or I just forgot the name of the airline in Europe, maybe Virgin Air. But there's been a lot of investment in airlines, or by airlines, in these technologies. So let's say we prioritize biomass for that industry, and we secondarily, in this scenario, consider that the heavy duty fleet could be really aggressively electrified. Then in the third scenario, we say, okay, let's prioritize aviation again, but also heavy duty trucking, and marine gets the last dribbles of the biomass. So in these 3 scenarios, we sort of laid out these options. So our methodology, basically, we have these scenarios. We have changes in the amounts and type of fuel year on year. To get to our environmental metrics, we need to pair those with life cycle metrics for each fuel. And these are metrics like kilograms of CO2 emissions per megajoule of fuel, liters of water consumed per megajoule of fuel. These are all housed in Argonne National Lab's GREET model. And so we pulled that into a GREET derivative model called Bioeconomy Age, where we match up those life cycle metrics with our scenarios and our consumption of fuel changing over time. And we're able to generate our results. So I will now describe some of those results. So in this figure, I'm showing the share of energy use. It's the share of energy use by sector, by scenario. So scenarios are across the top, but they're just in numeric order. So 1 is on the left, and then 2 is in the middle, 3 is on the right. So in these different scenarios, across all 3, we assume that the light duty sector would be aggressively electrified. And so in this instance, we hit about 50% of energy use in these sectors being electricity by 2050. But in the meantime, the other three sectors are where we're kind of playing with the biomass. And the one that's easiest for me to start with is the aviation sector in scenario 2. In this instance, we're able to get to nearly half of the energy use in aviation being provided from biomass. And then in this scenario is the same one we assumed electrification of the heavy duty fleet. That is about 27% of the energy use in that sector, whereas biofuels are around 15%. In the other instances, other scenarios, we're looking at roughly 26 to 28% of biofuels in both the heavy duty and the aviation sectors. Whereas in the marine sector, we start out, well, in this scenario is where it gets the last sort of dregs. This is 18%, and then we're at 21% in scenario 1. So overall, marine is seeing the least amount of biomass allocated to it. Now, if we translate this into the environmental metrics for these scenarios, these are the results. So we have greenhouse gas emissions, water consumption, PM2.5 emissions, and fossil energy consumption. These are provided at 2 different price points for biomass, $40 per dry ton and $60 per dry ton. So you're seeing the results for each scenario at those 2 different price points. But looking through these results, we can start with the blue line, which is the reference case, and that comes from the Annual Energy Outlook, the 2020 version from the Energy Information Administration. So we see that there is a decline in in GHG emissions because things are getting more efficient, but then we have an uptick in demand, and so we sort of lose some of those gains. The yellow line depicts when we electrify everything. So we have aggressive electrification in both the light duty and the heavy duty fleet. Based on this, we're able to achieve a 26% decline in GHG emissions from the base case. But you can tell that when we add biomass to the hard to decarbonize sectors, we can push that even further, an additional 11%. So this figure to me illustrates that, given the urgency of decarbonization, we should definitely leave biofuels on the table for the heavy duty sector, for the hard to decarbonize sectors. What's less important is how we allocate the biomass. So despite all the careful thinking we put into these scenarios and their development, the results are like roughly equal, regardless of scenario. So the good news is you can't sort of misallocate biomass. So from a policy perspective, you don't necessarily need to worry about what biomass goes where, we just need to use it. When we start looking at the water consumption metrics, though, things look a little concerning because our lowest water consumption is in the base case. So that is large, yeah.
Can I ask you a question?
Yeah.
So the first one, the greenhouse gas emissions, the first question is, I may have missed this, but what is the difference between scenario 1 and the yellow line, scenario 1 and the gray line?
Okay.
That's the first question.
Yeah.
The second question is, when you say you electrify everything, you probably get conditions, you must make some assumptions on the generation mix. And so what are your assumptions? Those could change your grasp.
Very true. Okay, so unfortunately, the orange lines are buried behind this. The orange lines are the $40 per dry ton price point for biomass, and the gray lines are the $60. So thanks for bringing that up because it's really hard to see. The $60 per dry ton. So basically, when you have the higher price point, you just get more biomass. Farmers respond to that market signal, and they have more biomass at the gate to purchase and then deploy. So like the lesson there is sort of the more biomass, the better in terms of decarbonization. About the electric mix, you're exactly right. We used the national average mix, but we did account for how that will change over time based on sort of projections, again, from the Department of Energy. So it includes still some coal, but natural gas and nuclear. So all those things, which is one reason why in the electrification case, we're seeing more water consumption. It's just really hard to beat the water efficiency of the fossil fuel supply chain, very water efficient. Anytime I do a biofuel analysis, the water always looks worse. And so this is something that continues to need addressing in terms of really getting at that water energy nexus. It's still a problem, still needs to be addressed. And so that's through things like fit for purpose water reuse within the power sector, for example, but also when you're looking at biofuel pathways, At least in my experience in working with technology developers, it tends to be a lot of focus on heat integration. We also want to think about water reuse and recycling within biofuel processes. Looking at the PM 2.5 results, when I worked at US EPA, I've learned that PM 2.5 emissions reductions carry a lot of weight because they're directly tied to mortality, and that translates into savings from a regulatory perspective and look at cost benefit analysis. So when there are PM 2.5 reductions, it's a win in the policy space, and also it's a win for human health. So it's good all around. But in every instance here, we are seeing results that fall below the base case. Now, the fossil energy emission consumption, of course, we want to see declines in fossil fuel use, but this result is pretty much the same as the GHG emissions because most of the GHG emissions just come from fuel combustion. So it's very, very closely tied. So, some of the things we thought about were like, well, wait a second, this is really going to influence refineries. And there are lots of people who do very detailed refinery analysis. We just looked at how demand might change. And what we have here is the reference gasoline line in the red line and the reference diesel case in the blue line. So the solid lines basically represent the reference case for all these different fuel types. So even if we just go the high electrification route with light duty vehicles, we have a significant drop in gasoline demand, which is unsurprising. But then as we decarbonize other sectors with biofuels as well, we see declines in overall demand for refinery products. So this is already a conversation within the refining industry in terms of how will operations be re-optimized, product portfolios be retooled. There might be an opportunity to refine some liquid biofuels or certainly do mixing on site. But one interesting feature of these results centers around the gasoline diesel imbalance. So in the US, we produce a lot more gasoline than diesel. And in these scenarios that we developed, no matter which scenario, that imbalance has been sort of addressed. So we have a much more even production slate among these different types of fuels. So the 500-pound gorilla in the room when we talk about biofuels is always land use. Land use is the most most prominent flashpoint around the debate of like, should we use biofuels or not? So of course we looked at this. And in the $40 per dry ton case where you're producing less biomass, you actually end up kind of even with your starting point in terms of land use. And the changes are pretty minimal. This axis doesn't go down to zero. But when we look at the $60 per dry ton case, we see at least a twofold increase in the amount of land that would need to be used to produce the biomass that we then use to decarbonize the heavy duty and aviation and marine sectors. So, if you just look at this number, like that looks bad. We don't want to necessarily convert our land to agricultural land. But the important thing is to ask, what kind of land is it? So in this instance, the energy crops we talked about at the beginning, they can be grown on marginal land, which is not largely used for agriculture. So you might ask, like, what is marginal land? And I had the same question as I mentioned, but in general, marginal land is land that has soil with lower carbon content, like lower quality soil. Yields tend to be lower. Farmers tend to leave that land idle if it's part of a farming property. And so there's a lot of room to use this land. I remember talking about this at a workshop at Purdue, like when I first started at Argonne, so in the 2010 timeframe. So this discussion around our use of marginal land dates back quite a long time. And in 2017, it really started to bother me, like, well, how much marginal land is there? What do we have to work with? So I started digging around, and basically different data sets have different numbers. As you can imagine, they define marginal land differently. So it's really hard to say. So we have a range we reported in 2017 between 59 and 127 million hectares of marginal land. So in this $60 per dry ton scenario, we're talking about using roughly a quarter of that. So we could, do this additional biomass production without sacrificing, without undergoing the agricultural land expansion that people so worry about. And because of this issue around land use, I have spent a lot of time, I'm a chemical engineer, but I spent a lot of time learning about how we estimate how much land we have in different uses in the US, because in my life cycle assessments, I've seen that biofuels have this potential to be really valuable contributions. They have the potential to give a valuable contribution to our efforts to decarbonize. So I really want to understand this land use issue. So I collaborated with several others on this evaluation of different data sources and their characterization of our land base, right? Because we really need to get at this if we want to know how our land use is changing. So we looked at 7 different data sources to see what they tell us about how we use land in the US. This is for 26, well, the data sets are, we got them as close together as we could because they're not all collected every year. So we have, these are the 7, and 3 of them are surveys that the USDA runs. So these are very highly regarded surveys, been going on forever, very high accuracy. We also have the National Natural Resources Inventory. This is run by the Geological Survey, again, very highly respected, long-term. They always look at the same land points every time. And so the longitudinal fidelity of these inventories is very high. And then we have 2 remote sensing products, the Cropland Data Layer and the National Land Cover Data Set, which the people then take the pixels from those satellite images and convert the information in those pixels to tell you like what kind of land is there. All of these data sets have error inherent in them, which we attempted to quantify in these error bars. But this is the error for a single point in time. When you try to do change analysis, the error just shoots up. So, but the main takeaway I wanted to present from this slide is that if we talk about agricultural land, we have pretty good agreement among our data sets because it is the USDA's job to understand how we're doing agriculture. So this is the primary focus of their work. When we get into grasslands, you can see there's a lot less agreement among these data sources. And so if you're doing a change analysis, it's going to matter a lot where you start and where you end with both your grassland and then your agricultural land. And this is where we start to see some challenges arising when people do change assessments. And finally, we have or not finally, but there's also a wetland category. It's not collected. This information is not collected by every data set. And then our woodlands. And you would kind of think that we might have a good handle on our woodlands, especially because there are machine learning algorithms to track forests using satellite imagery. But what I find very interesting is that this is the forest inventory analysis. So it's from the US Forest Service. It's their job to know our forests, and they're like the outlier. So it's just interesting to me. Again, my objective in running these numbers was really to kind of understand how different these different data sources present us with our understanding of land use in the US. And there's quite a lot of difference. I often feel like land use change analyses are presented as though they're like point of fact, and they're actually not. But because I've been kind of frustrated in this area and frustrated in like the limited accuracy in some of these data sets for these natural lands, that people are really concerned, and rightly so, about losing to agriculture, I started working with an electrical engineering professor and trying to use machine learning to find wetlands in aerial imagery that's very high resolution. So we devised an algorithm that's 98% accurate at finding wetlands in Illinois, where we had a really nice testing and training data set, which it turns out is somewhat unique to Illinois. But in these figures, the red is the ground truth that we obtained from the Illinois Natural History Survey. Illinois has a wetland bank. So if you are going to construct a roadway and you're going to wipe out a wetland, you have to then build another wetland somewhere else of the same size and quality. So they send people out with GPS backpacks. They walk around the perimeter of the wetlands to do these inventories. And so we had those data. We were able to construct our testing and training data set based off of that. But so this type of method, it has potential to increase the accuracy of how we're detecting these natural lands. And it all just ties back to, we want to be making good decisions about how we use our biomass. And if the land use consideration is the real sustainability question, then I think we need to keep doing a better job at characterizing how we use our land base. Because we really do need to set like these guardrails around, we don't want to, decrease the carbon sequestration in natural lands. We know they provide ecosystem services. We don't want to go off that cliff, but we need to better understand our land base still, even in 2021. So we're hoping to contribute to that effort. So these are my conclusions from this from this case study. And basically the nutshell is, I think that biofuels should be a part of this solution for decarbonization. And we have tools at our disposal to help us manage their growth and deployments to avoid undesirable effects like land use change that we might not want to see. So hopefully we'll be able to carry on with our efforts to do that. Okay, so now I'm going to talk about a different type of analysis. So the first case study was really life cycle assessment paired with scenario analysis. Life cycle assessment can tell you things like your GHG emissions, your water consumption. But what was starting to bother me was that it couldn't tell you the social effects that technology deployment is having on others. And if we talk about we need to increase our electrification, what was bothering me was that we know that we get half of our cobalt from the Democratic Republic of Congo. We know that around 10 to 15% of that is like mined by hand by around 110 to 150,000 miners. And it was bothering me that we couldn't put the social effects of that situation on a robust as level as we can the environmental effects. I've seen ELCA, environmental LCA used in policy. I would like to see the social effects, used also somehow in policy. So I started exploring social LCA in collaboration with an anthropologist at Northwestern, because I'm just an engineer. I needed a social scientist to work with me. This issue, for example, around cobalt, it's not new. I purposely include outdated news articles to show like this is known. And of course, it's not just automotive batteries, it's cell phones. I have a lithium-ion battery for my vacuum cleaner, like it's everywhere, right? So this is a known issue though, and it's not like no one's doing anything to try to address this. It is, but at the same time, when you hear people talk about we need to electrify for decarbonization, there's very little discussion about what that means along the supply chain. And so I again, hoping to kind of get this to a more robust level. So I started looking into social life cycle analysis, and it could be a tool that could provide more comprehensive effects, a more comprehensive assessment of these effects. But it's deceptively like similar to ELCA in its steps, but very different in terms of the metrics that are used. And some are easy to quantify, perhaps something like a fair wage or a fair salary or working hours, but some are much harder to quantify. So I talked to Sarah Young, my collaborator, and I said, I really would like to understand what you do, because she develops these, there are scales, they are cross-culturally validated scales to evaluate things like water insecurity. So they're quick, you can walk and talk to someone in like 5 minutes or less, have the information you need to, from that household to quantify their experience with water insecurity. And you can do that approach in any country and you will be able to compare your results. So this was news to me because I'm not a social scientist, that there are ways to do this quantitatively, defensively, and robustly. And so I was like, can we roll this somehow into social LCA? So that was the initiation of our conversation. Many of you may be familiar with the 4 phases of life cycle assessment. And again, the approach in SLCA is same 4 phases. But the key point here is that really after you get past phase 1, everything depends on phase 2. That's where you get your data. And if your data are weak, your conclusions are going to be weak. And it's that phase 4 where you're making statements that is meant to advise policy or meant to advise technology developers. And if you don't have good data in phase 2, whatever you say in phase 4 really loses steam. So this is the same garbage in, garbage out argument that we teach in process design, right? So it's the same concept. So sorry about that. I forgot about the whole Zoom bar thing. I don't think I can move it, but it's okay. It'll be okay. So the top basically just says we did some homework first. Like you can do that.
It's a spot so you can go all the way down.
There you go.
Oh,
It can also.
Can we minimize it?
If you go here, it should be right there. Hit this. Hide.
Hi.
Hit that and it should disappear.
There you go.
okay. I have learned something. Well, learned many new things today, but that was a new thing. After 18 months of Zoom. Okay. Now I know how to do it. Thank you. That was great. Okay. So basically we said, okay, how are we going to do this? How are we going to try to understand how we can use what you, Sarah, know and what I, Jennifer, know to improve phase 2 of SLCA? So we both started like doing some reading and we talked about being able to go to the Democratic Republic of the Congo and sort of explore different data sources that might be available. So she basically set up the social science methods that we would use for data collection, and we collaborated with a community college professor from Minnesota who's from the DRC, and he speaks all the different dialects and French. So he went and did the exploratory field research. This was in 2019, in case you're wondering. So it was before the pandemic. But he carried out informant interviews, focus group discussions, and participant observations, and collected all these data. But then we tried to view through the lens of social LCA, the different stakeholder categories, which include like the workers themselves, the community. And then through that, we wanted to identify opportunities to improve that data collection. These are pictures that Gabriel, our collaborator, took in Congo. And again, you know, some of these images could have come from reports 5-7 years ago. But the issues remain that mining is basically an integral part of the community in terms of there are mines right next to homes. There are mines within homes. Women aren't allowed in the mines. It's viewed as men's work, but the women wash the ore by hand in these ponds. And so then they have really high levels of cobalt exposure. And even though there are these efforts to reduce child labor, the young boy, this is a boy, he's a child carrying ore to be sold. So there's definitely still child labor. So again, we'd like to try and bring this into the decision-making process, or in a way that would help mitigate these issues so that we can carry out decarbonization without incurring these adverse social effects. So these are just some examples on the left of generic indicators in social LCA. So some of the terminology, like why is it a generic indicator? But this is the term in the official SLCA guidelines. So one generic indicator is child labor. And so we talked about using surveys to try and get at that, because if you talk to a company, or a lot of these there is no company, it's just people working on mines, you need to talk to individuals at individual work sites or in households to learn about child labor. But these types of surveys or interviews are time consuming and therefore expensive. So then there was a question, can we turn to publicly available documents like court claims to understand how people are being delocalized, like shoved off their land because there's a cobalt deposit there. So they're asked to leave and they lose their land. The safe and healthy living conditions generic indicator, one thing that Gabriel mentioned was that mining had pushed out some like small scale agriculture in the community. And so some people were needing to walk across international borders to purchase their food. And so we thought like, okay, we could take a look at cross-culturally validated scale to measure food insecurity to get at this. And again, that would be more rapid, more cost-effective ways of doing this, or using remote sensing on my earlier stuff. Like, can you just look at aerial imagery and see how land use has changed in these areas? And I think the one thing that really comes up a lot is that we need to have data at really a local scale. It's really hard for DRC to get data, but we took a look at iridium mining in South Africa. And just as an example, if you look at the national stats, we got 48% of people with secondary education, but in the mining region, it's only 31%. So this data that we need to do LCA needs to be at finer scales. There is publicly available country level data, but that's not going to tell you the story that you need to know if you're making decisions about how to improve conditions along the supply chain. Definitely need to do this with an interdisciplinary team. And I think, again, that this type of hopefully robust analysis should be filtered into the policy discussion along with environmental LCA results. This is my last one. My last method is material flow analysis. And so now I'm talking more about the material transition instead of the energy transition, and going back to that concept of circular plastics. So we have a project at Northwestern to look at building or designing polyurethanes that are more recyclable and have higher bio-based content. And so this is a collaboration with Argonne and with Dow. And my role in the project is to do the analysis piece, techno-economic analysis, life cycle assessment, but also material flow analysis. So what we wanted to do was build this material flow analysis to understand what is the situation with polyurethane in the US right now? Where is the low-hanging fruit? What are some guideposts we can help set up for technologists who are looking to devise like technologies that's going to make a difference in the very near term, both for incorporating more biomass and for enhancing circularity. So we started our MFA all the way at the beginning in terms of what do we make polyurethanes from. So unsurprisingly, we make them from crude oil and natural gas. On a mass basis, all these flows are in kilotons. On a mass basis, it's about the same, but from an energy content basis, the natural gas is about twice that of the crude oil. Then we take it to the next step and say, okay, well, what chemicals do we make from these raw materials? And that is these precursor chemicals, isocyanates and polyols, and also additives. Those are things like flame retardants that get mixed into polyurethane materials. So you're starting to track along here. You're saying, okay, we make a lot of polyethers. They're going into flexible foams, polymeric MDI into rigid foams. And then we need to see like, okay, where do these different materials end up in which sectors? So then that's the next stage. We label it manufacturing, but you can also think of it as the different sectors where we use these materials. We have a lot of imports coming in at this stage. So some of what's being made is basically out of our hands, right? We're importing it. And when you look next then at the flows leaving the manufacturing stage, this is what we've made from polyurethane in 2016. It goes into use. And then some fraction of it will go into the waste stream in 2016. So for a sector like building and construction, that's going to be a relatively small amount compared to what was made, because hopefully buildings last a while. So that things will be hanging out in a building for some time to come. Whereas the packaging sector, the lines are about even on either side of the use phase because packaging is short-lived. So what this ends up doing is telling us where are our waste streams predominantly coming from for polyurethane. And it's actually like relatively equal shares of things like furniture and bedding, the polyurethanes in electronics. So even things like speaker foam, for example, has polyurethane in it. Car seats, for example, in the transportation sector. And then carpet underlayment is a major category of waste. So we end up with around 2,000 kilotons of post-consumer waste, and we landfill the majority of that, of course. Incinerate a little bit. This data was from 2016, so we exported some. That's probably decreased, even though the number is already small. Now that China said we're not taking any more of other countries' plastic waste. So then we have this tiny little bit of post-consumer polyurethane that ends up in this very small glimmer of circularity that we have in the polyurethane system today in the US. So this is mechanical recycling. You can only do it so many times before things start degrading, and then you got to ship it off to the landfill. So overall, when you look at this and we think about the objectives of the project, which is increase bio-based content and increase recycling, like, okay, we should be able to make some headway here. Our baseline is very small, very low. But there are some challenges for polyurethane recycling if we especially if we think about mechanical recycling. So when we have products that have been around for a long time, some of the substances they contain are now banned. So these are some examples of those banned substances. So if you do mechanical recycling, whatever you're using that mechanically recycled product in, some of these compounds could be entrained. So that's a concern when we think about mechanical recycling of these longer-lived substances. If we think about, okay, like where is the low-hanging fruit? Where should we really focus? If we want to bring on board technology to enhance recycling and increase the circularity of the system, one thing that just jumps out of you is we throw away more flexible foam than we make, which just, okay, if we could recycle this, we could skip this part. And technology, glycolysis, already exists to really do this. It's commercially underway in Europe. And so the message is, let's see what we can do to get that here. So that's one example of very low-hanging fruit. And wouldn't it be interesting to redo this figure, which we hope to do, if this is all recycled? What would that look like? In terms of bio-based content, we said, okay, let's say you make all your polyols from biomass, then you would end up with polyurethane materials with this range, 7 to 65% of renewable contents. And if you swap that out to the isocyanates, you get a little bit higher range, 19 to 77%. So there are bio-based routes, these different compounds. We're continuing to explore different options within the project itself, but there is undoubtedly room to improve. So you could imagine pairing this type of material flow analysis with the types of life cycle greenhouse gas, for example, metrics I talked about earlier, and then sort of devising an analysis that quantifies in terms of GHG emissions what happens as you increase bio-based content and increase circularity. So this is something we plan to do for the future, taking into account the results of the overall research project to quantify the difference that we were able to make. So overall, I think that material flow analysis, this is the first one that I myself have undertaken. I think it's a very useful tool. It's very hard to do and it takes a very long time. So, but at the end of the day, the results are very informative. It turns out that there's only really a handful of plastics MFAs that we were able to find. Like, so our literature summary in the beginning of the paper is quite short compared to other papers. So there's still a lot of room to expand this area. I think that most of you in this audience would agree that to get to our next steps, to advance decarbonization, to advance waste reduction, we need these types of system level perspectives. And I think that that's the approach that we need to take to solve our most pressing problems. With that, I'd like to offer these acknowledgements for our funding sources and be happy to take any questions. I think I have to hit escape to leave the hiding thing so I can see the chat, if there's any questions in the chat. I'm gonna hit escape and hopefully I don't kill anything. But, oh, I didn't. Okay, all right, so yeah. Yeah.
I have a question about the polyurethane material flow.
Yeah.
So I'm just curious, how do you start to try to, I guess, find these values? Do you look through the literature or do you contact recycling facilities? Kind of how do you try?
Yeah, so for us, for this analysis, we had a lot of different data sources, but there were, I would say, 2 or 3 primary data sources. One was the American Chemistry Council has some information on the flows of polymers in the US. So that was a foundational report that we used. Also, for all the trade, there's the US International Trade Commission, and they have a host of data on like everything that's coming into the country and also leaving. The challenge, but it's not that simple because sometimes they'll put flows in monetary values. Then you're like, well, what's the market value of this entity of that, like a shoe, for example, right? So there's polyurethane in the foam soles of different athletic shoes, but okay, so if we have a shoe and we have a dollar flow, like how much are shoes worth, and then what portion of a shoe is polyurethane? So for that, we kind of leaned on some various market information, various industry reports. And so the supporting information for this paper is long because we wanted to be transparent about all these assumptions. So that was 2. Then 3 is other different industry sector reports. So I did not know this, but we collaborated with Dow on this paper. And so that was super helpful because they know a lot about this space. So they said, oh, there's a carpet cushion council, and they report like all these things about carpet recycling. I mean, I wouldn't have even known. I think our postdoc was Googling things like carpet recycling, but we didn't know there was a carpet cushion council. So it helps to have some guidance from people who really know the space to know where to turn. So those were our primary data sources. But when it came down to, again, estimating the mass fraction of how much polyurethane is in a car, like those are where you start to get into some differences. And there is a way in MFA to kind of manage the uncertainty and reconcile numbers that, oh, well, that's what the STAN software does, is helps you deal with the uncertainty in the data. Yeah. So there are two ways. One way is when I feel like I don't have enough data to even characterize the level of uncertainty. Like if I have a single data point for something. So for example, if I've just built a process model and that process model tells me I need so many megajoules of natural gas to get my product out, that's a single point. Now you could run Aspen and do some, sort of simulations with multiple types of inputs to get a range in that number. But that's still like coming from a model. So typically in that case, I will lean more on sensitivity analysis to just, again, more of the guardrail approach, like what's the maximum number this could be? So like maximum theoretical yields, that'll be like my best case scenario. And then like, what if we can only hit 20% of that or 10% of that? Or I lean on what I understand to be the state of technology for my like worst case scenario. If there's an instance where I happen to have a lot of data, which is actually somewhat rare when you're working with emerging technologies because they don't exist yet, then I can build a probability distribution function and do Monte Carlo. So that's my approach when I have enough data to do that. And then I think there are other ways to set up these tables that take into account things like how contemporary is your data set? Is it applicable for your region? Is it directly relevant to the system you're studying? There are 5 criteria. And then you kind of rate each data source based on that criterion. And then that factors into a standard deviation. That's the method that the MFA uses, but you could also use that in LCA as well. But I struggle a little bit with that because there's actually no physical meaning behind the plus or minus. If you use that, there's no physical meaning behind that. It's just your sort of interpretation of how well your data is representative of your system. And of course, different people could have different thoughts on that. So it's not like, you're working in a lab and you know that this instrument has a plus or minus and you can do error propagation. It's not, it's not like that. So I kind of, in some instances, I'd rather not do that and give some impression that I really know the plus or minus on a number. So even though like I often have gotten pushback in papers, like, where's your uncertainty analysis? You only did scenario analysis. And then I typically have success when I write as a response to that reviewer comment, like, we don't know enough about the data to generate a defensible uncertainty number. And that is why we are pushing on both sides of the best case and the worst case to kind of give a range. And sometimes I think that's the best thing to do, even though, especially in the age of data science, like people are like, where's all your numbers? But it's not always that easy. Yeah. Like in general? Yeah, no, I don't. I know that like when people were coming away from COP26, just whatever was that last week, people were saying they have hope. And so I think it's good to have hope, but it's also good to be aware of the technical and societal challenges of hitting that. And I might spend too much time with my friend in political science, so she may have colored my views. Oh, okay, I don't think that's, oh.
Is there a way to compare exploitation versus absence of technology? The example shown with the computer be better, the community be better in the presence or absence of mining. And we find, yeah, that was actually one of my questions too. Like, what metrics are you using to quantify the social impact? We talked a lot about data.
Yes. Okay. So to me, this is a question of how to set a counterfactual scenario. So what would happen if we weren't doing this? And this is, to me, one of the hardest things to do in analysis. And if you're reading someone else's analysis, it's one of the first things you should look at, because the benefit of the scenario you're saying you want or you're examining depends on what you assume for your counterfactual scenario, and people play around with that like crazy. have all sorts of unreasonable things. Some of them do a great job, but sometimes you're reading things and then you're like, there's no way this would ever happen in any like universe ever. So you have to be careful about that. And I think that would be especially difficult in the context of social LCA. So I don't think I would try to say what would happen if we weren't doing this mining. Instead, what I think would be, what I would like to see is a robust quantification of these social effects, whether it's through SLCA or ESG report or something transparent, that sets a benchmark, like here's where we are today with something like fair and healthy living or safe and healthy living conditions. And we've identified these things that need to happen to improve the situation. And then you go back like the next year and you measure again. That I think in the case of social LCA is a perhaps better way to approach it, because you'll never know what would otherwise be happening. And it's hard enough, like, you know, with scenarios like the IPCC does, like if we didn't do this, if we didn't do that, it's hard enough just with machines, but with people, I think that's a little bit, it would be very shaky ground. Of course, again, I'm an engineer and not a social scientist, and maybe people do this in the social science realm, I just don't know. But yeah, so I would handle it more through measurement. I did talk up to an economist friend who was saying there's like in economics, there's this concept of the, I think she called it the resource curse, where these opportunities that having these natural resources bring are good, but they introduce these undesired social effects. And so it's kind of this, I don't know, catch-22 is the right word, but it's hard to know what's really better. I think she said the same thing as she compared it to the garment industry.
I guess in this case, in the study that you did,
Yeah,
you showed us in chapter 2, case study 2.
yeah.
How do you quantify it? With the unity we're looking at, right? What is the metric we use to quantify the impact? That's an interview and gather data. but then
Yes.
What is the action?
So we did not actually do an SLCA. We proposed ways to improve data collection for SLCA because we would have needed a lot more resources to do a full LCA. So we had a seed grant and we're like, this is what we would need to do. And now hopefully we can apply for funding and do that thing. But let's say, so in environmental LCA, you have things like the GHG emissions, the water consumption, the air pollutant emissions, and some people roll those into a single score. And I always struggle with that because if you give, like for policymakers, it's easy to say, well, this is a 10 and this is a 90. So clearly you want to go with the better one, the 90, scored better. But that buries so many things that I don't like doing that. I've shied away from that this whole time. And with SLCA, it's even harder because you could envision like a single score. But if you're talking about something like food insecurity versus, what's another good one? Something like access to medical facilities, because sometimes mining companies will actually invest in the community and bring in these healthcare facilities that weren't there before. So to me, I would not want to like unify and provide a single score. I hate to use the word, but something like a dashboard or something like that could be helpful to sort of, again, like set these benchmark metrics and then track. But I think the key is in what data sources are we comfortable enough with to say we can use these to track. So like the UN Sustainable Development Goals, there's a lot of similarities perhaps. But when you did, I was like, oh, great, they're going to collect this data. But then you start looking at the website and there's like nothing there because people aren't able to collect the data and not at this level of like, you know, individual communities. So to me, it's something that we're really going to need to grapple with. I mean, even I was at a workshop about the circular economy of plastics. And someone said, well, in India, this would be a problem. I think it was, I may have misspoke. Let's just say Southeast Asia. Because there are people who collect waste and this is their livelihood. And if you take away waste, then you take away their livelihood. And so this needs to be considered. And this is something like you think, how can there be a downside to the circular economy for people? But there is. And so, yeah, I think that it's, you know, just, we have to try and think about ways we can bring that element alongside and with, you know, with as much importance as we look at all the carbon sequestration numbers. But it's not easy for for engineers to do, so we need to work with others, but I already worry about overwhelming policymakers with too much information and too many, like, it's this way if, or it depends. And then if you add this dimension, and it just makes it even more complicated in terms of decision making. So I think that's something else to keep thinking about. But yeah, I'm like letting my internal confusing thoughts come out of my mouth. So sorry about that. Oh. Oh, okay. Great. No.
No, I don't think so. I think, yeah, this
Okay.
was just thanking you.
All right.
Thank you very
Oh,
much.
thank
I'll
you.
stop sharing here.